Lesson 3.2, Atmospheric Mechanics. These are the terminal objectives. These are the enabling objectives for this lesson. In this lesson, we're talking about the general structure of the atmosphere and the major scale weather patterns, how they interact with each other, and the resultant effects on flight operations. This is an example of a station model. A station model is a quick look at what's going on at a specific point. There's a stick that points into the direction of the wind. In this case, the stick is pointing approximately 330. Therefore, the winds are coming from 330 because we always characterize wind direction as where it comes from. Speed is indicated by a quick glance at the barbs and or pennants, which are indicated coming off the stick. The pennant is the little black triangle that stands for 50 knots. A full barb is 10 knots and a half barb is 5 knots. So the combination shown indicates 65 knots of wind. And there it is spelled out. Present weather and sky coverage is shown on the left-hand side of the station model as well as the circle center of the station model. It will give the temperature, the dew point, the place where the asterisk is located, where will be a small symbol talking about the type of present weather. And then the sky coverage is indicated by whether the circle is filled in or not, or some amount of it is filled in. Pressure is shown on the right-hand side of the station model. It's given in millibars, but it omits the first 1 or 2 digits depending on the actual pressure. In this case, they're showing 1014.7 millibars, so you have to add the 10 to the front end and include the decimal point. Below that is going to be the pressure change over the last 3 hours, and then the trend for the pressure. So in this case, it has risen 2.8 millibars, and it's going to continue to rise. Here's a chart showing how to read the station model as far as sky coverage, present weather conditions, and tendency of the pressure. You do not need to memorize the chart, but it is good to note that whether it's an automated or a manual sky condition, it'll be a square or a circle, and then the amount that's filled in will directly relate to whether it is clear, 1/8 to 4/8 sky coverage, 5/8 to 7/8, or completely overcast. Again, you do not need to memorize all of the symbols. Wind is going to affect all aspects of aircraft flight operations. It brings about all of the changes in weather. The wind is moving around all the different water vapor or the moisture that's in the air. So it's causing and moving the fog, the clouds, and the precipitation. This image here is a snapshot of a surface analysis chart showing high and low pressure centers and then also those major frontal boundaries. Here's a closer look at that. The pressure distribution is shown on this chart by what are called isobars. Isobars are the long, thin black lines that you see circulating around the high and low pressure centers. Everywhere along that line is the same pressure, and the amount of pressure is indicated by its label, which is the last 2 digits of a millibar setting. So in the case of 12, that would be 1012.0 millibars. They are also spaced out in 4 millibar intervals. Highs and lows are shown in this manner with a blue high and a red L for low. The wind direction is going to be parallel to the isobars and clockwise around high pressure centers, as well as counterclockwise in the opposite direction around the low pressure centers. Right. The rate of change in pressure across a horizontal distance is called the pressure gradient force. The pressure gradient force will always act perpendicular to the isobars and thus will be perpendicular to the gradient winds, the winds that we just talked about that were parallel to the isobars. The more closely the isobars are located to one another, the more pressure gradient force is experienced. All right, so the more tightly spaced isobars mean more pressure gradient force and will result in greater wind intensity. So in this case, we have a low pressure center. The pressure gradient force acts inward towards the low pressure center because it is an ascending type of center, has less dense air that's rising. And so that pressure gradient force that acts in towards it, in this case, is causing more winds because it's a stronger force. So you see 30 knots. Also, you see an indication of wind direction coming from 270. And that is seen as the wind circulating counterclockwise around the low. Since we are south of that low pressure center, the winds would be flowing counterclockwise parallel to the orange isobars on this display. And so they're coming from 270. Again, the spacing of the isobars will indicate the steepness or strength of the pressure gradient force and the resultant wind. A wide spacing, in this case, there's no change to the wind direction. It's still counterclockwise around the low, and the pressure gradient force is still acting perpendicular to the isobars, but the wind in this case is only 10 knots because of the wide spacing and weak pressure gradient force. Here's another look at those depictions. As I mentioned just a second ago, a low pressure center is considered a converging or ascending type center because you have that low pressure air or warmer, less dense air that tends to rise, and when it rises, it leaves a void that air wants to fill in, and that is that gradient between the low pressure and the higher pressure air around it, causing air and the pressure gradient force to act inward toward the lows. Conversely, on the high pressure centers, those are colder, more dense centers, and so they have cooler, denser air, which is going to settle or descend, and then once it descends, it has to go somewhere, and so it spreads outward. It is diverging. So low pressure centers are ascending, less dense, converging type pressure centers with a pressure gradient force acting inward, and high pressure centers are cooler, more dense, descending, diverging pressure centers with a pressure gradient force acting outward. The gradient winds are what we spoke of earlier, and they are true. They are parallel to the isobars, but only when above 2,000 feet AGL. They will go clockwise around the highs and counterclockwise around the lows, but there will be a difference below 2,000 feet due to the force of friction. But just strictly due to the pressure gradient force and the Coriolis effect, the winds will blow parallel to the isobars as depicted above 2,000 feet AGL. Below 2,000 feet AGL, due to that force of friction, it both reduces the wind speed at the surface and below 2,000 feet AGL, and it also drags on those winds, causing them to blow 45 degrees across the isobars now when we're talking about surface winds. The direction that they shift in that 45 degrees is going to be dependent on the pressure gradient force. And in this case, the pressure gradient force is acting in to the lows, so the winds are canted 45 degrees inward toward the low pressure center, and the pressure gradient force acts outward of the high, so those surface winds are canted 45 degrees outward away from the high pressure center. The jet stream is a narrow band of strong winds found at the top of the troposphere. The average height is 30,000 feet MSL, and if you remember, the average height of the troposphere in the US is 36,000 feet, which allows for roughly 6,000 feet for the jet stream to exist in. As you can see in the top left-hand corner of the diagram, it is on average 3,000 to 7,000 feet thick. So that fits in there nicely, helps remember the other altitudes. It may be above or below this altitude depending on the latitude and the season, but its speed on average is between 100 to 150 knots. It may reach speeds in excess of 250 knots or more, and is usually no lower than 50 knots. So the overall range, 50 to 250, average is 100 to 150. As I said, it's 3,000 to 7,000 feet thick, anywhere from 100 to 400 miles wide, and 1,000 to 3,000 miles long, covering most, if not all, of the United States. The location of the jet stream changes position daily, and it's going to change the weather patterns because it is acting along with all the major air masses and low and high pressure centers. The considerations for the jet stream are going to be determining whether or not you will be in it and experiencing a headwind or tailwind, and the amount of turbulence that you may experience while passing through it. The video here is just showing how the position of the jet stream can change throughout the day and from day to day. Those are some major large-scale wind patterns. Now, local winds are dealing with, as it sounds, local winds. They are created by mountains, valleys, and water masses. The results, we get some general wind system development based on whatever the effect is, and it can lead to significant changes in weather, but they will act locally and not in the grander scheme as seen on the entire surface analysis chart of the U.S. Types of local winds include land and sea breezes, and this happens because as the sun comes up and begins to heat the surface of the earth, land will heat more quickly than the water. So if the water is cool, it will remain cooler longer, and the air over the surface of land will heat up more quickly and begin to rise. As it begins to rise, it leaves a void or a lower pressure area that will then be filled in by the cooler, more dense air that exists over water. So that breeze, that sea breeze, will blow from the sea onto the land during the day. And as that air rises up, it will cool down and start to become a little more dense and needs somewhere to go, but it can't come straight back down over land, so it will tend to spill back out over water, creating that circulation type effect that we see depicted in the graphic. The land breeze is the opposite effect happening at night. Once the sun goes down and then we no longer have that radiation type heating of the surface of the earth, the land will cool down more quickly, but the water will hold the heat longer. Therefore, the rising air exists over the water and the descending air exists over land, flowing from the land out to sea at night. So a land breeze comes from the land at night. A similar type effect happens with the absence of water, though, in the mountains and valleys. You can have a mountain breeze or valley winds. The valley winds are the ones that occur during the day. So as the sun is hitting the sides of the mountain ridges or the valleys, it's heating up the surface, and the air most close to the surface heats up first and begins to rise, kind of following the valley walls as it proceeds upward. The air in between the peaks remains a little cooler longer and more dense and begins to sink until it is then heated up. And so you get the valley wind flowing out of the valley during the day. At night, we get a mountain breeze. So the mountain breeze is happening because the air is cooling down, and as it cools down, it is going to rush down the sides of the valley and then down the rest of the valley down the mountain. It's cooled by that outgoing radiation and becomes more dense than that surrounding air. The initiating force for all winds is pressure gradient. Low pressure results from ascending air. The jet stream is the narrow band of strong winds found in the troposphere, where all weather occurs. Our next topic is clouds and moisture. These are the enabling objectives for this lesson. Moisture exists in three states, and we're talking about H2O here. It can be either a solid, as in ice, liquid, as in water, or gas in the form of water vapor. The atmospheric cycle is that changing in state between those forms. So evaporation and condensation is the most common form of that, and then once temperatures reach below freezing is when we start to see it in its solid form. This is the depiction of the hydrological cycle as it changes states primarily between a liquid and a gas, but again, it can result in freezing temperatures and creating frozen precipitation and or ice. As the sun heats up the water begins to evaporate into the form of water vapor. As that air rises and or cools down, that water vapor starts to come out of concentration and form clouds, visible moisture, and other forms of precipitation, which then falls back down to the surface of the earth and runs back out into the bodies of water or directly evaporates, continuing the cycle. Saturation is the point at which the air mass is holding the most amount of moisture it can possibly hold for that given temperature and pressure. The examples that we're looking at are the example of a 6-gallon bucket filled with 6 gallons of water and a 10-gallon bucket filled with 10 gallons of water. If these were to represent air masses, both of these air masses would be considered saturated, although it's obvious one air mass is holding more moisture, but that is due to its temperature and pressure allowing it to hold more moisture. The dew point temperature is the point at which saturation occurs. The higher the temperature, the more moisture that is currently in the air. The example that we see here is a 10-gallon bucket, but with only 6 gallons of water in it, meaning that that mass of air is capable of holding more moisture. So in this case, the dew point temperature would be lower than the current temperature. Once that bucket becomes filled up, and this could happen by evaporating more moisture into the air or lowering the temperature of the air, then it will again become saturated when it is holding all of the moisture it can possibly hold. The difference between the actual temperature or current temperature and the dew point temperature is called the dew point depression or dew point spread. Relative humidity is the amount of moisture the air is holding compared to the amount of moisture it could potentially hold when it is saturated. So anything less than saturation is considered relative humidity. In the case of the bucket example again, we have the 10-gallon bucket holding 6 gallons of water, so it's holding 60% of what it could hold, which would be like saying 60% relative humidity. If we were to lower the sides of the bucket, that would be like the same thing as lowering the temperature of the air, meaning that it could not hold as much moisture. If we lower the temperature or the sides of the bucket enough, it becomes equal to the amount of moisture it can hold, and it again becomes saturated. Now we're going to talk about the characteristics and types of precipitation. So once we reach and attempt to exceed saturation, there's nowhere for the moisture to remain in concentration anymore, and it comes out in the form of precipitation. Precipitation falls in these three ways that we list as the characteristics: showers, continuous, and intermittent. Showers are going to start and stop or change intensity rapidly, and they are associated with cumuliform clouds. Continuous precipitation will fall steadily. It will change intensity gradually, if at all, and is associated with stratiform clouds. Intermittent precipitation will start and stop, which is similar to showers, but it will occur at least once during the hour and could be either showers or steady, as in the example of continuous. Therefore, it can be associated with cumuliform or stratiform clouds. The types of precipitation are drizzle, rain, and frozen. The frozen precipitation, it's important to note, is already a solid. it is water in its solid form. The drizzle and rain can be freezing, meaning that they are at temperatures below freezing, but they have not yet become a solid or not yet frozen. For clouds to form, we must have condensation nuclei. Condensation nuclei are just little bits in the atmosphere of matter that allow the water to condense on them when the conditions are correct. These can be dust, ocean salt crystals, acid, salt, ash, and soot, and other organic matter. The water will condense onto these particles in the form of either water droplets or ice crystals, depending on the temperature. As we mentioned before, air becomes saturated by either cooling the mass of air to the dew point or evaporating more moisture into that same air mass. The principal cloud groups are as follows. Low clouds are clouds with those whose bases form between the surface and 6,500 feet AGL. These are a serious hazard due to cloud-based proximity to the terrain. The types of clouds in this principal cloud group of low clouds are either stratus, which produce steady precipitation, or cumulus, which produce showery precipitation. And these are two delineations of the overall stratiform or cumuliform type clouds. The middle cloud group is those with bases that form between 6,500 feet and 20,000 feet AGL. They usually are a light form of precipitation, and they get the prefix alto to differentiate them from the low cloud group. Therefore, we have altostratus, which would be that light and steady precipitation, and altocumulus, which would be the light and showery precipitation. High clouds are clouds that form with bases above 20,000 feet AGL, and they are composed of ice crystals and produce no icing or precipitation. The reason is because at those altitudes it is almost always freezing. Therefore, although they look like regular clouds, they are tiny ice crystals and not water droplets. These clouds receive the prefix cirro. So we have cirrocumulus clouds, which have a definite shape like all cumuliform type clouds. They are more puffy, billowy, and definite in shape. Cirrostratus clouds, which would be the more widespread, overcast, and indefinite type of shape clouds. And there's a third category to the high clouds, which is cirrus, which are the very high, thin, wispy looking clouds. Special clouds are the last type of principal cloud group, and these include towering thunderstorm clouds with extensive vertical development. The types of special clouds are cumulonimbus, a cumuliform type of cloud, the nimbus meaning heavy and violent. So these have heavy showers and they build upward. A nimbostratus is a stratiform type cloud, therefore it does not have the same upward building, but is still violent and heavy precipitation, although this time, since it is a stratiform type cloud, it is going to be characterized by heavy, steady precipitation, and it will be building downward. What type of cloud could produce towering thunderstorms with extensive vertical development building upward? That would be the cumulonimbus cloud, or thunderstorm. Three forms of precipitation are drizzle, rain, and frozen. The next topic is atmospheric stability. These are the enabling objectives for this lesson. The video here will show a demonstration of a stable atmosphere, or the tendency of something to be stable. And that is for it to return to its initial condition when it is first disturbed. In this case, the ball would roll up the sides, and then it would return back down to the center to come to rest from where it started. Neutral stability means that once a system is acted on, it has a tendency to remain wherever it was moved or changed to without wanting to return to its initial condition, like the stable tendency. And an unstable tendency would be that once the system is acted on, it continues to change and or move in the direction that it was initially moved, away from its initial condition, and continuing. When we talk about air and the stability of air, we'll first look about how air acts when it is lifted. Stable air would be air that is colder than the surrounding air after it has been lifted, and therefore, since it is colder and by definition more dense, it will want to settle back down to its original altitude and its original condition. Neutrally stable air is rare, but the same results are generally experienced as with the stable air. Once it is lifted, it is the same temperature as the surrounding air, and it will tend to remain at that state without continuing to rise or settling back down. And then unstable air would be air warmer than the surrounding air after it is lifted. The lifted air will continue to rise freely after the lifting force is removed due to that warmer temperature. The methods of lifting are as follows. Convergence is when two parcels of air interfere with one another, and where they meet, there's nowhere for the air to go but up, and so the air is lifted. Frontal exists typically in the case of cold fronts, because we have cold, dense air moving in a direction and replacing the warm air. As it moves, it is going to remain in contact with the ground and force the warm air up and out of its way. Thermal lifting is caused by the natural heating of the Earth's surface during the day. As the air close to the surface heats up, it begins to rise, and whether it continues to rise or not will be dependent on the rest of the conditions. And then orographic lifting is what we saw in the previous demonstration, showing stability. This is when an air mass encounters resistance due to some object or terrain. This chart shows the relationship between flight conditions and both stable and unstable atmospheres. All you need to do is look at the flight condition and read across for the associated condition with either a stable or unstable atmosphere. So in this case, a stable atmosphere has smooth turbulence, or no turbulence, or little turbulence. By contrast, the turbulence experienced in an unstable atmosphere would be considered rough. You can use this chart to determine the type of atmosphere or determine the flight conditions associated if given a type of atmosphere. The four methods of atmospheric lifting are convergence, frontal, thermal, and orographic. What defines air with the same temperature as the surrounding air after being lifted? Neutrally stable air is the same as the surrounding air after it's lifted. In summary, we talked about the atmospheric conditions, large-scale wind patterns, surface analysis charts, winds and patterns associated with winds, clouds and moisture, and atmospheric stability. A weak pressure gradient force would be indicated by a wide isobar spacing, meaning less pressure gradient force and less resultant wind speed. The forces that determine the wind direction in the atmosphere are weakened at the Earth's surface by the force of friction. Gradient winds move parallel to the isobars above 2,000 feet AGL because they are not affected by the force of friction. The air is blank when it contains the maximum moisture possible for a given temperature. That is the definition of saturated. What temperature must air be cooled to become saturated? to the dew point. The four principal cloud groups are high, low, middle, and special. If stratus clouds are present, you can expect flight conditions to be smooth in terms of turbulence and poor in terms of visibility.